So, thanks for sticking around. Now, this is a little bit unusual presentation, as you can imagine, because I see it now more or less like closing this book that we have seen over the last 3 days. And so I think I have the task now to just wrap up a little bit and summarize a little bit and then bring an outlook. And I will add a few comments from my own research, just a little bit, something that I feel hasn't been mentioned. And that's why I want to just share with you also my personal views. It's a little bit wrapping up what we've seen over the last 3 days and also where I see also the future direction with this. Okay, and that's why I call it, you are on this road to 3D nanomagnetism, and you're all on this road, and you're all invited to just keep going with this. Okay, so I hope that we all understood in all these wonderful presentations that we're really adding a new dimension to science, to nanoscience, to nanomagnetism when we now go into the third dimension. And for those of you who've been around, I mean, in the beginning there was always this, you lower the dimension, you want to go down deep and understand, you know, what's at the bottom. And I think I wouldn't say we've reached the bottom, but we've made a lot of accomplishments in nanomagnetism, in this nanoscale, in this low dimensional things. And all of a sudden realized, oh, we're missing a completely dimension, right? I mean, the world is 3-dimensional, 4-dimensional, of course, as well, but let's focus on this. And therefore, we're now entering this era, and you're all part of this. And I'm looking here at the students. I mean, you really are part of entering a completely new direction. And therefore, I would invite all of you, be part of this, be creative, be visionary. Again, the sky's the limit. Whatever you think, and we've seen all these examples, beautiful, but you see where the challenges are. This is where I need to go. This is where you need to finally go into deep and say, this is, I want to solve this problem. Okay, Laura also, towards the end of the talk, had mentioned, I think, a little concept that I also want to share with you, and I think we all appreciated this, getting together and talk and, you know, solve the problems by interacting with each other. So, and to me, this is kind of a magic triangle in order to really get a new accomplishment in science. And this is, of course, always this, what is it? Somebody needs to create the materials, and, you know, Amalie started in the beginning. This is how we structured this entire workshop here. Synthesize those. But of course, I mean, you might even start maybe with some ideas, a theory, a model. You've heard many of those, you know, computational efforts. There's also purely theoretical kind of considerations. And of course, the theory people will constantly talk to the people who make suggestions to the synthesis people and say, can you do this? This is what I think might be interesting. Vice versa, somebody who's doing synthesis might go back to the theory, says, oh, I created this. Do you think this makes sense? And then the next level in this cycle is, you know, no matter you have an idea, try to understand something, you create something, in the end, you need to validate. And this is the key. This is the key to finally bring it to something in the application. So this kind of circle, feedback, talking to each other, make sure, you know, we are on the same page with this, but also kind of motivate each other, right? It's not that the theorist only tells you what to do and you just basically go into the lab and do something. No, you are creative, you have ideas, and you go back, and then you go to the person who does the characterization, the validation, say, can you prove what I have accomplished? Is this true, right? This is really, I think, the secret. And the secret means that a community like we are here now, we need to understand you're not alone, and you need to reach out to others who help you with this. Okay, and then finally, again, this is really from understanding to controlling. Keep that as a bridge. So we want to understand it, and then we finally are able to control it. Or vice versa. Once you know how to control it, I think you know you understand it. Just you know, controlling it and don't know how it's working, it's not going to happen. Okay, I will focus in my presentation towards the end a little bit about some aspects of characterization, because I think really this is the bottleneck. This is what we need to go through no matter how we get there. Okay, and then of course we had heard throughout these 3 days, how do we get actually into 3D? And the first one, this was then Dennis' talk and others, you know, just a non-flat substrate, curve it, create a curvature, a twisting, or something like this. That's already the first step towards going into the third dimension, right? And we just saw like the buckyballs. Basically bring this 2-dimensional spin-ice system into the third dimension. So that's one way. And also, I mean, this book was mentioned. I just want to mention it again. But just very simple. just imagine two spins on a flat surface. They are parallel, ferromagnetic system, parallel. Put them on a curved surface, they might not be parallel anymore. Now, it's not that's not the same spins, but they might react differently. They might interact differently. And of course, we know something like a non-parallel ground state looks like a DMI. Now, I would say it's not a DMI, but it looks like. So there might be something phenomenal that you see by just basically put them on a non-flat substrate. Now, this could also be maybe this non-flat curved substrate, a design parameter in a technology, right? And we've seen these beautiful images from Dennis, for instance, on the finger, a little sensor there. Yeah, that's true. It might even go down to a non-uniform landscape, a defect somewhere. I mean, I know in industry, for instance, the people try to make these interfaces as smooth as possible. Maybe forget about all this, right? If we understand how a defect, a little bump on this device can be used, not just as a negative, but as a positive. See a defect to be something positive. But that means you need to understand that maybe you can position this defect at a certain place. And all of a sudden, your magnon might just walk around like this. We've seen also movies or some results from skyrmions going, I think what's called a helical track or something like this. And all these ones were going like this. I mean, take what you think is negative, take it as a positive. That's also something I would like to encourage you to think about this. Okay, and then of course, pretty clear when you go in 3D, you heard just the explosion of possibilities when you just go in a third dimension. It's not just a factor 2, factor 3. It's the possibilities of states is just exploding. And that means the complexity when you go into 3D is increasing. Chirality, it's here on my list. Chirality handedness cannot really happen in 2D. Right? And chirality is also a very fundamental principle in nature. I mean, we have a right hand, we have a left hand. There's, even in cosmology, there's kind of these things. So I think chirality, 3 dimensions, is clearly a path forward that we just need to embrace. And we've seen all these beautiful, I don't want to just repeat them again, very complex structures, and see complexity as a wonderful new opportunity. Don't say, oh, it's too complex, I don't understand it. No, embrace it. Embrace the complexity that comes with the third dimension, right? Frustration, again, we heard this morning all about spin-ice system when you go into 3D, the magnonics that links to this right away. Buckyball, we've seen it now so often. Beautiful, really, structures, and Claire's work and others. And I think, Amalia's just one point again. I think it's almost like a CAD design drawing that you can do more or less. I mean, I'm not sure whether it's true, but that's in the end, I mean, you have an idea, and maybe in the future, just say, okay, to your avatar, say, make this. And all of a sudden, you have an idea, and then you just take it into your research. And that should be really a lot of fun and excitement. Anyway, these were all these beautiful, or even more than this. And the 3D magnonics, we heard it again today. I can just flip through this. The magnonics as maybe a tool for the future of electronics. I mean, so far electronics means it's an electron moving around, right? And you have all these Ohm Schlosses and things like this. Maybe the future is go away from this concept of having an electron being the unit and use the wave as the unit. So lots of opportunities that you should embrace. I don't want to repeat all of this here. We've seen most of it here today. Now, topology, and again, I mean, John, a wonderful overview and also digging deep into topology. And there, I want to share with you a journey that I was glad to be part of since almost, about 20 years or so. And for those of you who've been around that long, we really all started more or less with vortices. I mean, we had this permalloy little disc carved out by even lithography. I mean, and we were fascinated by doing this. I still remember this wonderful science paper from Shinjo and Teruo Ono, which makes such a big achievement because all of a sudden you saw in a permalloy disc with an MFM in the middle, a black and a white spot, right? Beautiful. And then we started realizing, oh yeah, this is because the spins just follow this artificial kind of little structure there, and in the middle, in the center, because I mean, it's still a ferromagnetic system where the spins try to be parallel. It can't work because the circles get smaller and smaller, and the neighboring spins just become antiparallel. And the system just answers to that by pulling them out. Then you have this up and down and left and right. And then we thought about, oh, is this a new unit for computation? 1 unit, and you have 4 states that you can deal with. Then a little later, or 10 years later, actually, that's interesting. Look at the time scale. Every 10 years, there was something changing, I believe, in this field. Yes? safe travels. The skyrmions came along, and we heard a lot about the skyrmions, and I mean, Jiarong even showed us how they are topologically connected, right, with the defects, and there's really a trend that's coming, and then a couple of years later, around 10 years, I guess, now the hopfions are emerging. We don't even know where to look for them. I mean, Claire really nicely said we're still chasing them, but I see a lot of excitement about interest in trying to help finding those new features. And again, hopfion, just as a reminder, can only exist in 3D. There's no way to have a hopfion in 2D. Linking numbers, all of this. So, I mean, you know, there might be a 2030. I'm not predicting what will happen in 2030, whether topology has a fourth dimension. I don't know. You're the ones who finally will discover all of this. But this is also, for me, a very nice trajectory of how science really evolves. And being part of this, and I have to say, I personally, and many of you have been part of this, it was just a fascinating journey, right? I mean, starting from this very simple permalloy and now into this really very interesting and hopefully soon experimental confirmation of hopfions by knowing how to simulate them, right, Ricardo? Okay, good. Now, let me say one more thing. This is all about 3D nanomagnetism. Now, you might say, well, I might get into non-magnetism work. These topologic polarization textures have a counterpart in polar materials, ferroelectrics, multiferroics. So if you take home from now and you say, oh, my God, I mean, I got an offer to work with somebody on multiferroics, you might just probably see similar things, right? I mean, and this is beautiful work, again, from Ramesh and others, polar vortices in a multiferroic system. And then a couple of years later, they looked into polar skyrmions. And now this is polar hopfions. This is not yet experimentally verified, but it's just a matter of time, I believe, that somebody in this ferroelectrics, multiferroics community will also start looking into hopfions. And all of a sudden, you have a new friend, you have a new colleague that you can share your ideas with them. So again, that's what I'm trying to basically let you know about this, right? So now, okay, this is now where I really come in, visualization. And we heard, again, characterization. Seeing is believing. We still are human beings who want to see something, and then we believe it. Okay, this beautiful example, Röntgen, discovered in 1895. Accident. He was not planning to discover X-rays. He didn't even have a name for this. I mean, why is it called X-rays? He just had no idea what it is. It's X-rays, right? This was, in the first image that he took, I believe, that's what's reported, was the hand of his wife, right? And what you see here, well, the ring, right? And all of a sudden, he was able to look into this, saw the bones, because different absorption. So, Nobel Prize 1901. Not surprising, right? I mean, this was a groundbreaking thing. I mean, you can look through materials without taking them apart. You don't have to basically open the body. You just go through this. So, a hand, right? You would say, guess what? No, it's not. So, it's a rabbit. And what I'm saying here is that it's not enough just to have a two-dimensional projection. Imaging in 3D is a different animal. Right? It's really a different animal. And you need to do the imaging in 3D. We live in the three-dimensional world. One projection will not tell you the truth. And this is why now all this excitement comes about, all these tomography techniques. Okay, and now, X-rays, and this again, my own kind of contribution to this, where I've been working on for the last quite some years. X-rays are really powerful tools for magnetism. And those of you who have been in the X-ray business probably agree with this. What is really important, I think I want to emphasize this here, X-rays are element specific. They are able to probe in a multi-component system, pick up a certain element. Right? This is because the interaction between the X-rays and the material have these strong absorption edges. And I will show you one here right now. Right? So you choose a material, and this was like platinum cobalt, and you choose an energy, a photon energy, which you can get easily from a synchrotron or other X-ray sources. These are facilities. And you filter out simply one of these wavelengths. You shine with this wavelength on the material, and then you change this wavelength. And you will see a so-called absorption peak. And we call it here L3 and L2. Now, what is happening? Thank you. The X-rays come in, and the binding energy of an inner core electron, in that case, at this energy 778 or so, matches exactly the binding energy of a so-called 2p3 half electron in cobalt. It's not in iron. In iron it would be different. In nickel it would be different. In gadolinium it would be different energy. So by picking this color of the X-rays, you are sensitive to only that element. That means if this is in a large collection of any materials you have, you go through this because of penetration power and you pick up this signal. Now, for magnetism, and this is what I want to point out here, is you have so-called extramagnetic circular dichroism effect. And you heard this throughout the talks. I want to get you back to the basics of this because you need to understand what are we actually measuring here. So what we're measuring here, we come now in with a circular polarized X-ray. It's not any X-ray, it's a polarized. It has a certain sense of polarization. And let's say we come in with a negative helicity, negative or positive, that's what you can do. And then you come in, now this helicity is basically an orbital momentum, right? And you absorb, the photon is being absorbed when it has the right energy, right at, let's say, this 2p3 half electron. It gets absorbed, you deposit this energy, you deposit this angular momentum, and it ejects basically, or it transfers this 2p3 half electron in the absorption process into a state at the Fermi level. That's exactly what the binding energy is. Now, then depending, of course, on the density of states at the Fermi energy, your absorption coefficient, the number of photons that are being absorbed, will change. If there's more density of states, you have more space to put this electron. If there's less, you have less. And then in magnetic materials, ferromagnetic materials particularly, you have a difference between what's called the majority band and the minority band. The spins that are pointing up or the spins that are pointing down. And they have different density of states. Now you come in with a certain helicity. You pick up, of course, a certain electron, exactly the 2p3 half. This is not anything else, very element specific. And you populate this. And then basically, when you count then the difference between left and right, negative helicity, positive helicity, this is where the magnetization is parallel or antiparallel to the helicity of the photon. You have different absorption profiles. And look at these numbers here. Huge effects. These are big effects, like 10% or more than this. And that is then in the end what's called the XMCD signal. It's basically the difference between those two absorption profiles plotted and occurring at the L3 and the L2 edge. Now, one thing very important. What is the difference between L3 and L2? L3 means you're probing the 2p3 half electrons. L2 means you're probing the 2p1 half electrons. What is the difference between 2p3 half and 2p1 half? Simple atomic physics. Electrons have a spin and an orbital moment. When it's parallel, L plus S, spin-orbit coupling, you have P is 1, S is 1 half. 1 plus 1 half gives you 3 half. L minus S gives you 1 half. So what you see here is this difference between those two edges is nothing but the spin-orbit coupling. And spin-orbit coupling is a fundamental phenomena in magnetism. We've heard about this. We heard about orbital moments. We heard about orbital contributions and all of this. Orbital momentum is related to anisotropy, a fundamental magnetic property, ground state property. So what you're probing with these polarized X-rays, with the XMCD, is element-specifically, quantitatively, the magnetization of your material. Very important, right? Why is it even quantitatively? Because you can calculate in so-called sum rules, you use the area underneath this XMCD signal from the L3 and the L2, the spin L plus S and L minus S spin-orbit partners, and you build from that, you can calculate from them simply a quantitative measurement of orbital moment or spin moment. It's very simple. The L plus S minus the L minus S, gets away with the L or the S, and you subtract it and add it. That's it. It's very simple. Very simple experiment, but very powerful. And when it started in around, mid-1985, first experiments, 1992, these so-called sum rules were developed by Teodola and Carrà. This is when I started my PhD. This was just mind-blowing. You can measure fundamental, element-specific magnetic ground state properties by a simple experiment. How many photons do you send to the sample? How many photons come through this with the polarization? And this has really taken off. Okay, so much about it. And you can do this quantitatively for ferro and ferrimagnets. Antiferromagnets, which we didn't discuss too much here, but I'm pretty sure this will come to this community as well, can be measured by what's called an X-ray magnetic linear dichroism. There's a slightly different approach, but you have the Néel vector, parallel or antiparallel or 90 degrees, and you get also some contrast. Okay, very important. So, but keep in mind, element-specific and quantitative. And this is, I want to really stand out here. In 3D, We have to take advantage of this more and more. Okay, so this is another beautiful example showing the power of these XMCD techniques. Old work from Pietro Gambardella, right? I think at the time when he probably was a postdoc, ESRF, I guess, many years ago. What I want to show you here is the following. What he did is he used this XMCD spectroscopy, what I just described, and looked into a system that was either bulk cobalt, a three-dimensional bulk, a two-dimensional monolayer of cobalt platinum, a single one-dimensional atomic chain, or a single atom. So from 0 dimension, one-dimensional, two-dimensional, three-dimensional. And you might say, does that make a difference? It makes a huge difference when you look at these L3 edges here. They start growing. That means you get more orbital momentum when you reduce the dimensionality. So simple experiment, and you can even see how the dimensionality is reflected in the magnetic ground state properties. Right? And just imagine, this is now the tool that you have to throw on your magnetic systems and then analyze it. Right, so the increase of orbital momentum, solid state physics, textbook, you see where it's coming from, but you can measure this. Okay, and this was then also used, and we heard from Claire, the magnetic X-ray microscopy is imaging, seeing is believing, and there's a lot of tools right now available. Don't want to go through all of this. The most recent one, I think, are the ones that are working more or less in reciprocal space. There's also direct imaging techniques. They use some lenses, optics, or photo emission electron microscopy. Powerful tool as well, but the ones that take advantage of coherence, and that's my next important point to make here, is these are the ones that Claire showed, like the tachography and the laminography and all those very interesting new techniques that are just emerging, and they really are fully leveraging this increased coherence that we're seeing more and more from X-rays. Okay, coherence, keep in mind, coherence is the future. So, and then just think about what you can do with a coherent beam, with a coherent probe. As a kind of a model for you, look back about 60 years ago when lasers were invented, optical laser. And just imagine what you do these days with lasers. Just imagine the time, 6 years ago, there were no lasers. What would the people not be able to do? And what can they do today? Starting from eye surgery and, I don't know what else, right? I mean, you measure, a distance in a room, you're no longer taking the tape measure, you shoot with a laser on it, right? Okay, so keep in mind, the coherence is absolutely important. And then we've heard from Claire particularly these capabilities to go into 3 dimensions. We do tomography. There's, of course, the direct imaging, and then there's even more this laminography and the nanotomography with tachography. Basically, you basically rotate the sample around and then do some really sophisticated analysis. I mean, all these beautiful images that we've seen yesterday, it's a lot of data. A lot of data, a lot of analysis. But the more we get used to this, the more standard it will be just to analyze those. Okay, now this tomography, and this is again not nanomagnetism, but also shows you what the potential is. You can, for instance, look into microchips with these techniques. Microchips is a real device. Some people try to reverse engineer and try to understand what's going on there. Or is there a defect in there? Why is the microchip not working? Well, you do something in this tachography, tomography setup, and then you put in a computer, and you basically go through this on the computer. You don't have to take it apart. I mean, and this should be doable in the next couple of years because of the new sources that we will be seeing that are coming up, upgrades of the synchrotron source, particularly within minutes. So this is then will be. I mean, this of course from Holler at the PSI back then was probably a couple days of pioneering experiment. The future, when you get into this field, I can tell you, it's a matter of minutes, and you just do it, standard, and do all of this. But you really see all the details. The element-specific component comes in. You can just focus, let's say, on a copper and on things like this. Okay, now, my own contribution that I want to share with you as well, and this is really this showing you how important it is to measure and quantitatively determine, let's say, the texture of a skyrmion. And what we've been doing is we used a regular cobalt, iridium, platinum system that was E-beam lithography patterned into a disk about 100 nanometers thick and about 800 nanometers across. We knew there was the so-called target skyrmions. We were looking for skyrmions and hopfions. But what we did then finally is we put them into the laminography, in this tomography tool set at Swiss Light Source. And we ran it for about a night, data set. And then my student actually took the data home and came up now with a rendering of the fully 3D kind of representation of the spins, of the texture in this little disk here. Right? And you've seen by Claire 5 micron, big chunks of material. This is pretty small, but I think it's relevant. Right? This might be the length scales that in industry might be relevant to develop some tools with this. Okay, and once you have this in the computer, then you can take slices, and you can, for instance, plot the MX component, the MY component, the MZ component, because it's all in the data now. Just start analyzing the data. You make slices on this. What you can do even more, now you can slice through the stack. Right? You just take the slice. We've seen a couple of those examples here. And then you can see how, for instance, at the top, at Z equal 80, it looks like, and down to the bottom. And then you go and slice it through this and have volume cells, and you analyze all these volume cells. And what we found, and this I think was really interesting, we found like the evolution of the winding in the skyrmion is not uniform across the entire stack, which I felt, probably not surprising, but still nobody has ever seen this, nobody has ever measured this. And what we found is here, like this is at the bottom, Z equal 20, 40, 60, 80. The rotation happens differently. Now what is it? It's basically reflecting the actual, at each volume cell, energy landscape. So maybe at the bottom it's a little bit slower to rotate, and at the top it's a little faster to rotate. Of course, you can derive from there like a barrel structure. We've seen this as well. Then my student was also able to basically analyze this kind of domain wall chiral character there. Basically what he did is he just plotted an angle. In the computer you can do all this, and he found that primarily this is all Néel walls. Again, in each voxel cell, the colors are the different depths. Right? So you have a depth resolved quantitative analysis of a skyrmion. You basically dissect the skyrmion in its entire structure in 3D. And lastly, we were able to quantify even because there was a relationship between, let's say, the PMA energy density, Heisenberg energy density, and the DMI energy density. And of course, we did not determine these K, A, and D values. We just took it as, said, that's the material, let's take them. So we can't really measure the fundamental materials parameters, but we could measure the profiles again. And you can see there's slight variations when you go through the entire stack. Okay, this is, I call, a quantitative nanometrology of a skyrmion with a pretty good spatial resolution. Okay, future directions. Again, those storage rings will come more and more. They're already here. In a couple of years, the world will be full of them. Until then, there might be a little bit of dark time. So if you plan, but now it's time to think about this future direction. And then, of course, I think in the end, it will come down to we want to do a multidimensional magnetic X-ray characterization across all the scales, space, time. We've seen this. So we want to control the flow of non-collinear plane textures in a tailored 3D geometry, nanostructures. We want to particularly look at interfaces. I said it already a couple of times. The interface is the device. And of course, it's not from me, but that's keep in mind. You need to understand interface. You bring one material next to another one, and you want to see what is changing. And we see this throughout all the simulations. Interface, interface, interface. Okay. Coherence, last slide here. Gianluca, I'm done. Coherence really enables X-ray vortex beams. Now, this is a fascinating topic, and I highly encourage you to think about this. Vortex beams are beams with orbital angular momentum. And like an X-ray, normally a photon has 1 h-bar. But with the new coherence, we will be able to generate X-ray beams, photons, where each photon has more than 1 h-bar. Planck quantum, right? Now, what does that mean is you will be able to make spectroscopy, the one that I showed you earlier, which was the P to D kind of transition, a simple dipolar. So you basically have 1 h-bar, deposit it, you have a simple dipolar transition. But there might be states somewhere higher, F states, G states, H, you name it. These are totally inaccessible as of today. There's no way that with one spectroscopy shot you get there. In the future, we'll get there. And I can guarantee you, you will discover new phenomena. I mean, there's no doubt about this, right? If you want to do this, that's the future. And this can also be done with electrons. So there has been shown coherent electron beams in the TEM, transmission electron microscopes, carry large orbital angular momentum. Ben McMorran, like up to 100 h-bar in the electrons. There's also, I mean, this is copying what has been done again with lasers, in the optics community, photonics. There's a lot of, vortex beams there. But again, for X-rays, it could be something like, can we transfer this orbital momentum to the magnetic material? You deposit it, and you might see something changing. You might see something, I think one of the questions we ask here, to be something like a helical structure that will benefit from this in a certain way when you come with the orbital angular momentum in one way or the other way. So a lot to explore. Okay. Interferometry, again, I just want to say there were two major experiments of the last 100 years, I would say, that all used interferometry. Michelson and Morley was the proof for a relativistic theory is correct. C is constant. Interferometry, LIGO, was the proof of gravitational waves. So both of them, I think, got Nobel Prize. So if you're up for Nobel Prize, think about, can you do X-ray interferometry? Now, what is the difference? X-rays have a wavelength of an angstrom or nanometers. Precision of LIGO in an X-ray interferometry experiment, just do the math, you will be able to probe length scales of about 10 to minus 30 meters. Just think about what you might be able to do with this. Right? Okay, so I'm done. If you are interested in a postdoc position at Berkeley Lab, just have an opening right now. Apply by May 15th deadline. Anyway, and with this, thank you so much for coming to this workshop. I hope you enjoyed it as well as I did. I think it was fantastic. Nanomagnetism 3D, I think this is just the starting of more to come, and I hope you all will be part of this. Yes, and that was it. Thank you so much.